Hello, today we will be talking about Treaps, a very interesting algorithm that combines aspects of data structures that we have learned in the past. Treaps were first described in 1989 by Seidel and Aragon, and its name, as well as its basic functions, are a combination of tree and heap. Essentially, it is a binary search tree that utilizes randomness to keep itself balanced, similarly to splay trees. There are several advantages to Treaps over other data structures. For example, the code is much simpler than that of AVL or red-black trees, and Treaps also support bulk operations that other binary search trees do not, such as split and join. The nodes of a Treap have two values, a key value and a priority value.
The key value is the same as in any BST. For any node, all nodes in its left subtree have smaller key values, and all nodes in its right subtree have larger key values. The priority value is a value that is randomly assigned to each node, and they are arranged in a max heap. So for any node, all nodes below it have smaller priorities. Without priority values, a set of keys can correspond to a multitude of BSTs, some of which are degenerate. Priorities allow us to uniquely specify the shape of the tree, which is the key property of the Treap. Using this randomness, we are avoiding degenerate cases and are very likely to have a height of O of log n on average.
Treaps support many different operations. It supports the basic BST operations such as insertion, deletion, and search. Treaps also support bulk operations such as split and join. Given a value v, we can split a Treap into two, the first one containing all nodes with keys less than v, and the second one containing all nodes with keys greater than v. Or we can do the reverse by uniting these two Treaps through the join operation.
Searching for a key value is performed in exactly the same way as in a regular binary search tree, starting at the root and going either left or right, depending on the key value of the node we are at until we find the node we are looking for or hit a leaf.
Rotations are essential for supporting the insertion and deletion operations. They ensure that the BST and heap structures are maintained. For example, let's say that the tree on the left respects all heap and BST properties, except that the priority value of W is greater than the priority value of U. By rotating to the right, we can restore the heap property while maintaining the BST property. Similarly, we can do the mirror image of this move in case it is the other way around.
To perform insertion, first we insert the new node at the bottom of the tree, similarly to a regular BST insertion. Then we restore the heap property of the Treap by rotating the node upwards while its priority value is bigger than its parents. In this figure, we insert the new node with key value 80 and priority 12 at the bottom of the tree, in the position that maintains the BST property. Since its priority value is larger than its parents, which is 10, we do a rotation. After that, its parent has a priority of 15, which is larger, so we stop here.
To delete a node, we must find it and then move it down until it is a leaf. To do that, we repeatedly rotate with the child with a higher priority until the node to delete is a leaf. In this figure, we are trying to delete the root node with key value 50 and priority value 15. The left child has a priority value of 5, and the right child has a priority value of 10. Since the right child has a higher priority value than the left child, we rotate left to maintain the max heap property. We repeat this process until the node to delete is a leaf, and then we can finally remove it from the tree.
To split a Treap as previously described, we insert a dummy node into the Treap with a key value of v and a priority value of infinity. Thanks to the heap property, it will end up as the root of the tree, and thanks to the BST property, its two children will be the two Treaps we were looking for.
To unite two Treaps, we must create a dummy node with a key value of v and any priority value, v being the key at which you want to unite the two Treaps at. We assign the two Treaps that we want to join as two children, and then we can delete this dummy node from the newly created super Treap.
The Treap supports many other operations. All other regular BST operations like finding the kth key, the minimum or the maximum key in the tree are supported by the trap as well. We can easily print all elements of the trap in sorted order in O of n. We can also build a trap from an array in O of n, although this is harder. Another very important but more advanced operation is merging any two traps of sizes m and n in O of m log n by m. which is the optimal complexity and has a surprisingly easy and efficient code. Unlike the join operation, the merge operation does not assume all keys in a trap are smaller than all keys in the other.
This is a table showing the complexity analysis of treeps. We can see that on average, all operations run in O of log n time. However, the worst case time complexity is O of n for all operations. This slide shows the complexities of 4 different data structures: treeps, simple binary search trees, AVL trees, and splay trees. Even though the treep shares the same average and worst case times as a regular binary search tree, it is much less likely to run into a degenerate case using treeps, similarly to splay trees. To measure the actual time cost of treeps, AVL trees, and normal binary search trees with real data, we implemented the 3 data structures and ran them on the Emory Computer Lab using AVPN. Our input accounted for arrays of 5 different sizes, and they were all run under 3 circumstances: a randomly ordered array, a sorted array, and an almost sorted array. We inserted all elements from the arrays into each data structure in the given order and measured the total time for insertion as well as the maximum height of each tree.
The first test was on an array of random elements, and as you can see, all 3 data structures perform similarly. The AVL tends to have a maximum height of about half that of the other 2 due to it not relying on randomness, but still takes about as much time as the other 2 due to its higher constant from dealing with harder rotations. The advantages of traps and AVL trees become clear when we ran on an input of sorted elements, where the regular BST will always end up degenerate. The Treap does not suffer from this problem due to the priorities balancing the tree. Even when the input is not perfectly sorted, the regular BST struggles, while the trap has no problem keeping up with the AVL. Thus, these experiments show that the trap has no problem keeping up in performance with other trees that are much harder to code and analyze, like the AVL tree or the red-black tree.